Welcome to our astronomy class. This is for the spring and winter. It's actually winter now, January 23rd. This is, excuse me, for the winter and spring semester of 2020. This is astronomy. Class number PHY350. My name is Kammerer. And there will be bookkeeping type details for the course that we'll discuss as the semester moves on, such as will there be tests and quizzes? The answer is yes, but we'll get to that as we come along. Will there be practice, otherwise known as homework? Yes, we'll discuss that. I will say now that the homework will be on D2L, so you can avail yourself of the practice/homework on D2L. If you have any questions or any concerns, or you can't find something online, certainly please come and see me. If you see me in the hall in class, please come right in and let me know. Or you can email me via the email on the D2L. But we're going to get right into astronomy. I guess the most practical question to start with is, what's astronomy about? So I'm going to ask that question again, and then I'll be quiet, and you could come up with your own answer. What is astronomy about? Most people, when they get asked that question, say, well, astronomy is about stars and it's about planets. True. But that's a little bit too narrowly focused. In the big, broadest sense, astronomy is about everything. Astronomy is about the world on a very large scale, like millions of miles and billions of miles. Astronomy is about things on a very large scale distance-wise. It's also about things on a very large scale time-wise. So you might say, well, that star is 50 trillion miles away from us. That's a really large distance. Then you might say the sun is 5 billion years old. 5 billion years, that's a really big time period. So astronomy is about everything which I'm going to call the universe. It's generally about things on a large scale. Not always. Sometimes we'll talk about things on a smaller scale, but a lot of astronomy is about things on a very, very large scale. At the beginning, here in our first class, I'm just going to go over a road map, or a map of what astronomy is going to include. Kind of what this would be is a map of the universe. not in great detail, but just in terms of the basic moving parts. I'm going to start with something we're all familiar with, planet Earth. Obviously, this is not drawn to scale, and I'm going to write this down. I'm not going to write it down all the time, but it's important to realize that these diagrams are not to scale. I mean, we just said everything's gigantic, so it's, of course, it's not going to fit on a little old board. There's the Earth, to give some numbers, or one number. The diameter of the Earth is about 8,000 miles. That's a big number. I mean, you fly from New York to Miami. It's about 1,200 miles. Here we're talking about 8,000 miles. 8,000 miles is big compared to the numbers we normally use on a daily basis. So there's the diameter of the Earth. That's part of the universe. We're going to take a series of steps where we look back and try and look at things at the bigger scale. So we're going to back away from this. And if we back away from this, we're going to find out that the sun might be there. This is way, way, way out of scale. The distance from the sun to the Earth, since we're talking about distances, sun to the Earth is about 92 million miles. So in this general map of the universe, we have some distances and some things that are things. I'll use a different word more. There's a thing called the sun, a thing called the Earth. The sun is a type of a star, the Earth is a type of a planet. And we'll come back to that vocabulary. Sun, Earth. In this map, everything is moving. I mean, you could go, like right now, it's like 10:40 on Thursday, January 23rd. Go out right now and say, oh, the sun's over there in the sky. It's standing still. It's not standing still. It looks like it's standing still. It's really moving. Everything in the universe is moving. Even things that look like they're standing still, they're not. They're really moving. It's like an optical illusion that makes them look like they're standing still. The Earth is moving. The Earth travels around the sun. So the Earth goes around the sun. The Earth orbits the sun, which I'm thinking you already knew that. In this map, we're going to take a quarter of a day. No, you have 3/4 of a day extra. Year 4, another quarter of a day. Now you have, well, 3/4 of a day plus another 1/4 of a day. After 4 years, you have one whole extra day, because even though a calendar has 365 days, it really takes this long to go around the sun. After 4 years, you have an extra day. Let's take that to be 2020. So if you go back 4 years, 2020, now we have an extra day. If you look at a calendar for 2020 and you count the days, 2020 does not have 365 days. The calendar year 2020 has 366 days, because there's that extra day. That extra day is placed in the calendar next month. Normally February has 28 days. February 2020 has 29 days. The origin of that leap year, leap day, February 29th, is this. This is where the term year comes from. A year is how long it takes the Earth to go around the sun. All right, that's part of the map. You probably knew this already. All right, we're backing up. We want a bigger and bigger view of things. We're backing up, we're backing up, we're backing up, we're backing up. What are we going to see? Well, we're going to see this. We're going to see here is the sun, and there's a planet here orbiting the sun, and this planet is planet Mercury. Mercury is the closest planet to the sun. Then we'd see there's another planet. Again, this is just a diagram. This doesn't mean this is exactly where these planets are. That would be Venus. Then we'd see another planet. That would be the Earth. And so on. There are 8 planets orbiting the sun. If you don't know, I'll mention it now. Pluto doesn't count as a planet anymore. Pluto is still there. Pluto still goes around the sun, but it doesn't count as a planet, even though 20 years ago it did count as a planet. Astronomers got together and they said, well, let's take a closer look at the solar system and define what a planet is. And they said, well, a planet's got to be kind of on the big side. If there was a rock like this big going around the sun, a rock this big, no one's going to call that a planet. But if you take a rock bigger and bigger, how big does something have to be before we say, hey, we should call that thing a planet? This big, no. This big, no. A rock this big, no one's going to call that a planet. Well, Pluto did not make the cut. Pluto is not, in those astronomers' view, big enough to count as a planet. So consequently, we now say there are 8 planets. Pluto is still there, but it's just not counted as a planet anymore. So this collective map here, This is called the solar system. Which I did not spell correctly. That's the solar system. I'm continuing on a theme, backing up, backing up, backing up, walking backwards, getting a bigger view of everything. Eventually, in this map, you would see the Milky Way galaxy. Which is basically just a collection of stars, billions of them. So you have a group of stars, billions and billions of them. It's thought to be about 200 billion stars in the Milky Way galaxy. And they have a shape. The shape of the Milky Way galaxy is kind of like a spiral. All these dots are supposed to represent stars. I mean, it's crazy drawing this, but I will for now. This is a view of the Milky Way galaxy. All those dots represent stars. The solar system, our little old solar system, including our home planet, Earth, is in this universe. So there's billions of stars. Nobody knows exactly which one it is, but let's say there's a solar system. The solar system has its home in the Milky Way galaxy. That's part of the map, looking at a galaxy. It's billions and billions of miles across here. We're not going to write down any numbers because I don't want to get too much into numbers here at the beginning. But this is obviously really, really large. Not only is it large, but this whole thing rotates. The whole Milky Way galaxy rotates. You'll see during the semester that rotation is very common in the universe. All the planets rotate around the sun. The entire Milky Way galaxy rotates about the center. So here's another view, a larger view of this map of the universe. We have the Milky Way galaxy. All right, let's keep backing up, get further and further away from this. I'm going to erase this. And back up even more. And then we can say, all right, this little thing here that represents the Milky Way galaxy. But you know what? There are many, many other galaxies. There are billions of other galaxies. So I'm just going to draw one other one. Let's say over here, there's another galaxy nearby called the Andromeda galaxy. And again, I'm drawing these curvy lines. Those curvy lines represent stars. There are billions of stars in the Milky Way galaxy. There are billions of stars in the Andromeda galaxy. But there are other galaxies. I'm not going to put names down. Here's another galaxy. A lot of information here in class 1. There are basically two shapes for galaxies. Galaxies are either spiral-shaped or they're shaped like balls or globular. It's just like a big sphere of stars, star, 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 star. Billions of them in like a big old ball. That's another type of galaxy. But in this bigger picture, again, with stepping back and looking and looking and looking, there's other galaxies. So I'm just going to draw some other galaxies in here. And this whole collective thing of galaxies there's about 20 galaxies grouped together. Now we're talking not right next to each other as a group, but they're kind of together. The distance between these galaxies is billions of miles, trillions of miles. But they are, in a sense, grouped together. Kind of like, you know, you could be in the cafeteria here, and there could be 5 students sitting here and 4 students sitting together here. There's a group of 5 students. There's a group of 4 students. There's a group of 4 students. Well, there's groups of students. Well, here's a group of stars called the galaxy, another group. So you have a group of, sounds redundant, you have a grouping of groups. So you have about 20 galaxies grouped together. And these 20 galaxies grouped together, including our home galaxy, the Milky Way galaxy, this has a name. This is called the local cluster. It's just a cluster of galaxies. They're not touching each other, but they're in one grouping. And if you got back far enough, you would say, hey, you know what, there's a grouping of things there. They're all kind of in the same spot. All right, so in the map of the universe, we're now up to the local cluster. We're going to take one more step backwards. So let me erase this and say, if we were like super far away, way, 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 way far away, and we look at the universe, what are we going to see in this map? Well, you might see something like this. You might say, this is the local cluster. But there might be another cluster over here. And there might be another cluster over here. This gets a little bit on the crazy side. So you have a bunch of stars together forming a galaxy, but then you could have a bunch of galaxies together forming a cluster, but then you could have other clusters where there's a bunch of galaxies over here in this cluster, and there's a bunch of galaxies over here in this cluster. And there's pretty much emptiness in between the clusters. Huge, huge amounts of emptiness, trillions and trillions of miles. I'm going to say that one of the requirements for astronomy is you need a really good imagination, because you can't comprehend this. I mean, you know what a mile is like, you know what a foot is like. If I said to myself or to you, what's a trillion miles like? I have no idea. I've never seen a trillion miles. None of us ever will see a trillion miles. I can see 100 feet across a gymnasium or whatever. I can't see a trillion miles. But in astronomy, we're talking about gigantic, gigantic things. There are questions that come up, which we'll answer during the semester. How do people know this? I mean, it's not like I can find out about a country. If I want to find out about London, I can just fly to London and find out about London. When I say let's step back and look at a bigger view of everything, that's strictly imaginary. No one's going to get in a spaceship and go way, way out and look back and see this. But this is what we know based on very clever scientists figuring this out. This is the ultimate map of the universe. I'm going to put down a question. Where is the edge? To give an example. If I take this is a foam core board. It doesn't matter. Just call it a piece of cardboard. If I say, well, where's the edge of this piece of cardboard? It's right here. Cardboard, cardboard, cardboard. Come over here. And now it's not cardboard. Here's the edge of the cardboard. Here's the edge of the cardboard. So I say, all right, make believe this cardboard represents the universe. It's not going to be shaped like this, but it's going to just be clusters of galaxies. Where's the edge? There's no answer to that question. This is where your imagination comes in. There is no edge. It's not like you say, well, if I go 100 trillion miles, I'll be on the edge of the universe. Nope, doesn't work like that. The concept of edge doesn't pertain to the universe. So that seemingly simple question doesn't have an answer. It goes, and then that's it. But it's not like, well, you go to the edge, and there's something on the other side. Nope, that's not going to happen. There is no edge. And we'll talk about that during the semester. The other question, which does have an answer, is how old is the universe? It's about, I'm going to say about, it's about 12 billion years old. That's a gigantic number compared to numbers we deal with. If a human being lives to be 100 years, that's a long lifetime. 100 years is nothing compared to the universe. If we talk about civilizations where human beings developed farming techniques and developed ways to live together in a community and support each other. So again, civilizations. Civilizations go back 5,000, 10,000 years. So human beings have only, not all parts of the world, but the first human civilizations, the Assyrians, etc., go back 5,000, 10,000 years. That's still nothing compared to the age of the universe. If we take our solar system, the sun with the planets going around it, how old is our solar system? The solar system is thought to be about 5 billion years old. That's B as in boy. It's about 5 billion years old. It's still a lot less than 12 billion years. That's the age of the universe. Now, we said this question doesn't have an answer. There's a lot of questions in astronomy where people don't have the answers yet. But one question that comes up is, well, what was there before there was the universe? I mean, if you're saying the universe is about 12 billion years old, what was there 13 billion years ago? The answer is nobody knows. That's where, again, goes back to your imagination. If you say, what was there 13 billion years ago? Nobody knows. It's strictly an imagination thing. It's kind of like saying, if you're 20 years old right now, and someone says to you, where were you 25 years ago? You say, I wasn't even born yet. But where were you? You didn't even exist 25 years ago if you're 20 years old now. Well, that's kind of like this. If you say, well, the universe was quote unquote born about 12 billion years ago, but what was there 13 billion years? It didn't even exist. I don't know. It wasn't there. The question really doesn't make any scientific sense. So back to your imagination. Not all the questions, not all the ideas in astronomy are going to be, oh, I get it, that's like driving a car. Or I get it, that's like how high the ceiling is. Some ideas in astronomy, you have to have a really good imagination, which is a good thing. It's good to cultivate an imagination. So this is our first little video portion of the class. I'm also going to put some reading assignments on D2L. Let me write this down. Because for this class, the videos, etc., if you're watching this, you already know about D2L. So please see D2L for other readings, assignments, etc. If you have any questions, you can certainly email them to me via the D2L. Or if you see me walking down the hall, just say, oh, I'm in your astronomy class and you spoke about universe in class. Could you explain what this means? Certainly, please stop me if you see me. So I wish all of you a very good semester. Any help I can be to you, certainly please let me know. And I look forward to seeing you next class. Some numbers for time and some numbers for size, numbers for distance. The Earth orbits the Sun in approximately 365.25 days. Once every 365.25 days, the Earth goes around the Sun. That orbit is not a circle. It's an ellipse. And we'll come back to these topics. The things I'm mentioning now, we will come back to during the semester. I just want to give like an overview, or the word I used was a map. So the Earth orbits the Sun in 365.25 days. Now, if you look at a calendar, if you looked at a calendar from last year, 2019, and you counted the days, January 1st, January 2nd, et cetera, you'd end up with 365 days. It does not take the Earth 365 days to go around the Sun. It takes 365.25 days, so a little bit more. There would be confusion if every year had 365 days. The confusion would arise from this. If in year 1 there was an extra quarter of a day, fine. After year 2, there's another extra quarter of a day. So now you're up to a half a day, because a quarter of a day plus another quarter of a day from year 2, you have a half a day extra. Then you go to year 3, another extra